Okay, more with the radical functions unit. This is 5.2, and we're doing some operations with radicals. Mostly we'll be multiplying and or dividing radicals, sorry. Quick reminder, if you have root A times root B, it is equal to root AB, if and only if the insides are non-negative. Now, I know we've been doing real expressions so far. They're in 5.1. We might open it up just a little bit and allow some negatives inside the even roots, just to keep things lively here. But let's take a look at a couple examples here right now. So let's see, if we have root 5 times root 50, obviously, square roots, you're looking for pairs of things, and there's a couple different ways you can look at it. These are both positive values, and one way you could just kind of charge straight ahead, and you could actually simplify both radicals first. Of course, root 5, you can't simplify root 5, but root 50 is 2 times 5 times 5, so that would be 5 root 2. Now, typically we do the outside numbers times the outside numbers, so there's a 1 in front of this root, even though it's not written. So 1 times 5 would be 5, and then root 5 times root 2 is root 10. And you look and we go, okay, we can't really simplify that anymore. So there's the answer to that. Now, just in case you were thinking, well, I could have done it a different way. Yeah, there's different ways you can do it. Another way you could do it is you could actually say this is root 5 times 50. Now, yes, I know we're multiplying, but we're also going to be looking for pairs of things, and so why actually do 5 times 50 if you're going to be breaking it down looking for pairs? So why not start breaking it down immediately? I mean, it's already broken down some, 5 times 50, and of course 50 is 5 times 5 times 2, and so we have a pair of 5s. Pairs go out on a date, so 5 root 10. And look, we got the same answer. I mean, we should get the same answer. It's the same problem. A couple different, so really there's more than one way to do the problems usually. Okay, let's take a look at the next one. So again, outside numbers times outside numbers. So you got the 7 times 2 is 14. And then we have 6 times 15. Now, again, don't multiply it out. Yes, we know it's 90, but don't break it down, or don't make it 90. We're going to break it down anyway. And if you wanted to, even as you're writing it down, 6, of course, is 2 times 3. So you could have just gone 14 equals, and then 6 is 2 times 3, and 15 is 3 times 5, and we've got a pair of 3s, and so they go out. Now, that would be 14 times 3 root, and then 2 times 5. And so 14 times 3 is 42 and root 10. And right now it looks like every answer is going to be root 10 at the end. No, sorry, that's just coincidence. Let's try another one. Now, what if we did have some negatives? And don't let it upset you too much. I mean, if we're doing some operations with things, we should be able to handle the fact that if we have some negatives happening, we can deal with them. So just a quick reminder up here in the reminder section. If we have square root of -1, of course, we know that the square root of -1 is the imaginary unit, and so that's equal to I. And if we take it a step further, if we square that, I squared is -1, and so on. Now, we're not going to do very much with this, but we should be able to handle it. So let's say we had square root of 6 times the square root of negative 12. Okay. Well, we can't use this first property here, the root A times root B, because they're not both non-negative. So we have to deal with the negative. We have to deal with the negative on the 12 first. So this is equal to root 6 times, now negative square root of negative 12 would be I root 12. Okay, now once we actually deal with that, we can now do outside number times outside number. So we have 1 times I, that's I, and root 6 times root 12. Now, you can even do something like this. The 12 is obviously 2 times 6, and since we're multiplying, aren't we going to have a pair of 6's there? So, times 6 root 2, which is 6I root 2. Let's try the next one, number 4. Okay, so square root of negative 18 times the square root of negative 2. Now, if you were not paying attention and you just multiplied and you didn't pay attention to the fact that the insides have to be non-negative and you just multiplied, you'd get square root of positive 36, and the square root of positive 36 is 6. But we are paying attention, and so let's deal with this. The square root of negative 18 is I root 18, and the square root of negative 2 is I root 2, and I times I is I squared, and then we have root 18 times root 2, which is root 36. That's not bad to go ahead and do it this way this time, because we can see that root 36 is 6. So we have negative 1 times 6, which is obviously negative 6. Now, like I said, don't freak out too much about it. There's very little of the negative stuff in there, but you should be able to still handle that as we're going along. Okay, let's try the next one. Let's say we have 3, now not everything's going to be square roots. So 3 cube roots of 16 x to the 4th y times 2 cube roots of x y squared. Okay, so basically it's the same rule. So if we have cube root times a cube root, you do the outside numbers times the outside numbers and the inside numbers times the inside numbers. And now when we're doing, again, when you're doing odd roots, positive, negative, that doesn't really bother us one way or the other if it's an odd root. So outside number times outside number, we got 6, and then I've got cube root. Okay, now again, why multiply things all the way out if we're just going to be breaking them down anyway? Of course, 16 is 2 times 2 times 2 times 2, so 4 2s. And we have a total of x to the 5th, so that would be x to the 3rd times x squared, kind of emphasizing my 3 of a kind stuff here. And then I have y to the 3rd. Okay, so I'm noticing I have 3 of a kind on the 2's, I have a 3 of a kind on the x's, and I have a 3 of a kind on the y's. And so we have 6 times the 2 and the x and the y come out, so 2xy cube roots. Okay, what's left behind? 2x squared. Okay, final cleanup here now. So this would be 12xy cube root of 2x squared. Okay, next one here. Number 6. So let's say we have root 6 times root 6 plus root 18. Okay, so again, pretty basic thing. Yes, there is some distribution going on here. Now, root 6 times root 6, isn't that a pair of 6s? Yes, it's a pair of 6s. They would go out. So that would be 6 plus, okay, root 6 times root 18. Isn't that root 6 times 6 times 3? Yes. Pair of 6s there. So this would be 6 plus 6 root 3. Okay? It doesn't simplify any more than that. Is it possible to factor out a GCF of 6 there? Sure. Does it help us to simplify it? No. So you certainly don't need to factor out that GCF of 6. Okay, now let's talk about the rationalizing denominators. Rational means, we just finished a whole unit on rational expressions. So it's a rational number in the denominator. Now, the reasoning behind that comes from before calculators, really. And so before calculators, if you're doing a fraction, you're really doing division. And you want to divide by a rational number. You certainly don't want to try to divide by an irrational number because there were no calculators. So why do we still do it today? Well, there's a lot of things that just get cleaned up nicely, and it's still an important process for us to be able to do, to recognize things, mathematical expressions, in a more cleaned up version. So it's just something that we still need to be able to do. As you get to higher levels of math, it's not as big a deal about having denominators rationalized, but it is still important on occasion to be able to do it, and so we need to be the masters of it. Okay, so let's say we have problem number 7 here, and let's say we have, I don't know, 6 over 5 root 2. So we'll just start just real basic here. Okay, so can't leave a radical in the denominator. Okay, now is the 5 a problem? The 5 isn't a problem. Okay. So the root 2 is what the problem is. Now, to get this to become a rational number, I would need a partner for the root 2 so that the 2's can come out of the radical. Okay. Now, you have done this before, so we're just discussing the basics of it. Now, if I'm going to multiply, I can't just multiply the bottom by that. I'm changing the original expression. So I have to multiply the top by the same number so that this actually reduces to 1. If I multiply by 1, I'm not changing the value of the original expression. I'm just simply changing what it looks like. So we go ahead and multiply. The denominator, outside number times outside number, so 5 times 1 is 5, and root 2 times root 2 is 2, because there's a pair, it goes out. Now the top is 6 root 2. Okay, now we always reduce fractions if we can reduce fractions. Okay, now yes, I know 5 times 2 is 10, but it is in factored form, and doesn't the 2 go into 6 evenly? Yes. So let's reduce. So 2 into itself once, 2 into 6 3 times, and so final answer here is 3 root 2 over 5. Okay, square roots. You're used to that kind of thing. So let's try another one here. Let's say we have 2 over the cube root of 5. Okay, now just real basic stuff here. What's the issue? We have a radical in the denominator. Okay, so I want it to become a rational number, so I need the 5 to come out of the radical. What would I have to multiply by? Well, if I multiply by the cube root, because it has to be a cube root, if I multiply by the cube root of 5, how many 5s do we have there? We would only have 2 5s. And how many 5s do we need to have to come out of the root? We need 3 of a kind. So 1 5 right there would not do it. We need 2 5s. So you're going to multiply by the cube root of 5 squared, or, of course, 5 squared is 25. So I'm going to multiply by the cube root of 25 so that I have a total of 3 5s there, and it'll come out of the root, and that means I have to multiply the top by the same thing. So I'm multiplying top and bottom by the cube root of 25. And if I do that, I get 2 cube roots of 25 over 5, because I've got my 3 of a kind there right now. Okay, so obviously, if it's a cube root in the denominator, you need 3 of a kind for it to come out of the radical. Okay, let's try another here. If we are rationalizing the denominator, so it's a 4th root of 27. So 4th root of 27, that means there's already 3 3s, you know. So really, we need 4 of a kind for it to come out. So if we multiply top and bottom by 4th root of 3, that would give us 4 3s there, and that would come out of the radical. And so we have 3 in the denominator, 6 times the 4th root of 3 in the numerator. Of course, it is a fraction, so we reduce if we can. And I notice that 3 goes into itself once, and 3 goes into 6 twice. So final answer is 2 times the 4th root of 3. Okay, last problem, number 10. Square root of 6x to the 4th over the square root of 5x squared y to the 5th. Okay, now this square root over square root, so obviously we can put it all inside one big fraction, inside one big radical, which means that we can reduce. Essentially, it's inside things with inside things. And I noticed right here that x squared, we could reduce an x squared in the top and the bottom here. So x squared, and I get x squared up top. Okay, so now, as far as rationalizing goes, I would need a 5, so a pair of things. So I would need square root of 5, and y to the 5th, that's an odd number, so we need an even number of things, so we have pairs. But I would really only need y to the 1st. I don't need to do y to the 5th, just y to the 1st. And so if I multiply top and bottom by root 5y, down in the denominator, we would get 5, and I have y to the 6th, so that's y to the 3rd times y to the 3rd, so y to the 3rd. And then I also have up top, I have root 30x squared y. Okay, one last double check here, and 30 is 5 times 6, 5 times 2 times 3. X squared, that's a pair of x's, so that can come out. So x root 30y all over 5y cubed. Okay, nothing else reduces or simplifies, and so there it is.